Hi guys, so it seems not too many folk were up for the first session for whatever reason. Hopefully more of you can join us on Monday next week. I thought I'll take just a few minutes anyway to record myself talking to myself so that I can communicate a few things and help us get into it. So I'm just checking what's happening here. Nothing, okay. Right, so I'm just going to be sharing my screen, so I'm going to minimize this a little bit. And I've just got the Moodle site open over here, so close this. So you should see something fairly similar. As the tutor's view, you'll be able to see the module outline. Okay, and the important things will be, I think a few of you wanted to know the dates, so that's the important parts there. A blog course on the 4th and 5th of October, and then the second one on 21 to 23 November. 23 is a Friday, and almost certainly we'll be able to arrange that exam for that Friday afternoon, and we can use the Friday mornings for Friday morning for revision. Okay, you'll obviously see other dates for the assignments along the way. So we're going to have assignments on DC machines, on transformers, on induction machines, and on synchronous machines. And a little bit in the mix along the way on special machines such as stepper motors and servo motors. More about that later. Okay, important things to note. Let's see. There is a final written exam, 50%. The pracs, you need to attend the pracs there in the block courses, obviously. And then there'll be some time for you to write prac reports on those, not necessarily all of them, but the attending of those pracs and the submission of the prac reports will be combined 20%. And the assignments is shared fairly evenly amongst that, 30% is shared fairly evenly amongst those. A couple of important things. Overall, we do need 50% or better, but you also need a sub minimum of 40% in the final exam and 40% or more in the internals, which is the assignments and the lab course. So just bear all that in mind. The rest down here is more general information, which I don't think any of you have studied at WinTech before. That'll be much the same as what's in everybody or the other tutors' course outlines as well. I'll just mention here about our books. So you will have seen that I sent you already a number of chapters from Bird. That is from this one, I believe. This book here is essentially the same book. At the end, it's got a few extra chapters on some maths and not really necessary for our purposes anyway. So whether you're using this one or this one, it's really the same thing. Just this one is available electronically through the library. The other one, and hard copy, the other one's available only as hard copy. But what I've done anyway, through the library, it's available for online reading, which is a bit slow when you're scrolling, which is why I've generated those PDFs, a certain number of pages that you can use to generate a PDF, and they're enough to cover all the chapters that we need. So I've generated those and sent them to you so that it's much easier to scroll through there. This one, Worldy, what I'll be doing there is giving you a I'll be giving you a link to a PDF. Kind of should make the PDF available itself, copyright purposes, but it does seem to be freely available on the net. And I'm sure you can find it just as easily as I can, but I will give you a link there. But we'll only use that a little bit later when we get to the section on transformers. Because Bird has transformers as well, but I found Worldy there a little bit more useful for our purposes. Okay. Right, so that's the module guide. I can shrink that down. We will roughly try and keep to this schedule, but it might not be precise. It's the schedule I'm talking about. This one, let's try and shrink this touch. Okay, so we will follow this today effectively with the introduction of fundamentals. We'll look at DC machines that with motors and generators. Then we'll jump to transformers, induction motors, and synchronous machines in that order. Okay, I'll minimize that. And I've got open here, let's see what else is on the Moodle site. So that's where you'll find the forum. We'll post things to that fairly regularly. Nothing there yet. Those should come to your email. There should be an sort of a notification in your email that there's been a post. Generally it tends to attach everything and include the message in the email anyway. But if you want to be able to see them all in succession, in a series, at least you can go and look in the forum posts. Okay, what else? So there'll always be this little Zoom meeting link at the bottom there. If you click on that, you should be able to, okay, it'll be for me to start the meeting, but it should take you to somewhere that you can just hit that join link. It'll be the same link as what I typically email though, just as a reminder. The link will actually end up using the same one over and over because each week I'll just be updating the meeting as a new meeting with a new starting time, which typically will be 6 o'clock Monday nights. Okay, that's the Zoom meeting. Let's go back. Right, assessments. That just tells you pretty much the same thing as there was in the module outline. We're going to have the labs, we're going to have assignments, we're going to have the exam. There are some previous exams which are already on here, but I'm going to be adding some more, including last year's exam at some point as well. And when I say last year, I actually mean last semester. There is one from last year as well, which was for the on-campus students. That will be also fairly useful for me to include there as well. Review, that's what we want to get into really. And as the review mentions, we're going to look at motors, generators, transformers. We want to sort of change this to student view instead of my view, but it doesn't really matter. You can have a look at this fundamentals lesson and the electromagnetism lesson. Fundamentals lesson, a little bit in there about forces and angles and radians per second and accelerations and various things, and torque being cross products. I would say I'm going to talk in a few minutes. I'm going to draw up some sketches on this touchscreen that I'm using, and I'll try and highlight the important things there anyway. So if that's not all making total sense to you, don't worry too much. There's a bit extra there that you don't really need. I'll highlight the important things. The electromagnetism lesson is a pretty much good overlap between that and these 3 chapters in Bird. Okay, but use it as a supplement Bird with that. But I think Bird is perhaps just structured a little bit. Yeah, it is a textbook after all. It has more to say, but it will probably be a little bit clearer, and some of the terminology is a little bit different, but by all means use both. So where were we? Back to there. All right, so I'll jump in a minute into this review of electromagnetism, and then from next week on, hopefully, we'll be able to jump into DC motors and generators. Oh, that's not scrolling. That's interesting. There we go. Okay, there are some readings there for you. There's a bit I've put on here about energy, work and power, calculation of mechanical power, efficiencies. I've got some examples also on efficiencies and calculation of power, etc., which I'm going to post to the forum. There's another little video for you as well, a couple of bits and pieces down here to supplement. But we'll also have these chapters in, not these chapters, but there'll be chapter 26, I think it might be, in Bird, which I've actually already emailed you guys, that you can have a look when we get to the motor section. Okay, so I just want to go through now this magnetic circuit section to try and highlight the important things for our purposes. A little bit of summary over here. Define the terms. And then I'll talk a little bit about the mechanical aspects as well, forces and torques and things like that. So you all know a fair amount of magnetic theory already. But here's the main things that I want to emphasize. Flux density, B in Tesla, an important term. That fire symbol is the flux itself. Let's see. Okay. Flux is really just the term that we use for the actual amount of magnetism present, if I can put it that way. We obviously need to create that magnetism using generally electromagnets, so we're going to have a number of turns around some kind of a magnetic material, and we're going to have some amps flowing through that. But a magnet itself could be a permanent magnet, even it will have a certain amount of flux, and then the area is the cross section of that magnet through which that flux is I want to use the word traveling, but it's present in that cross-sectional area. I'll show you a little bit more about what we mean by that in a minute. Magnetomotive force, or MMF, it's really the driving action behind these things. We know if we have a force, a cause will have an effect. So typically in the same way as volts in a circuit gives us an effect which is current, in the same way our driving force typically in a magnetic circuit is amped turns. So N is the number of turns, I would be the number of amps, and if you multiply those two out, you're going to get the magnetic driving force. So we'd have some kind of a metal magnetic circuit, some coil around there. If you have a lot of turns, you can feed in a small number of amps and end up with a large magnetic driving force. Otherwise, if you only have one or two turns, you've got to feed a lot of amps through there to achieve the same thing. It doesn't necessarily require a lot of power, though, to put all those amps through, because amps power would be product of volts times amps. So they don't have too much resistance, because you don't have that many turns. You can still actually get a lot of you can get those amps flowing relatively easily. I just contradict myself there, because whatever amps you need, you'll need, that's right, you'll need less volts if you don't have much resistance to get the same amps. So you don't necessarily, you're not necessarily using a lot more power by having more amps. But typically, you want less amps and more turns will do the same thing, because then you can have thinner wire with less amps and less resistance of those wires as well. Okay, so amp turns. Then we have another thing, which is the Where is the definition? H, which is the amp turns per meter. There it is, the magnetic field strength. So that's the amp turns per meter. That per meter is per meter of the magnetic circuit that we have. So a metal material that you've got windings around, some part of it or all of it. If you take the sort of center line of that magnetic path, that's the L that we must use in here. Okay, then we have an important relationship, that is this flux density that is produced. So if we have a certain magnetic material and we force a certain magnetic field strength on it, some amp turns per meter, we will end up producing a certain flux density. If we make that area of the magnetic circuit wider, surface area that the flux are getting forced through, we'll actually end up with more flux, because it's the flux density remains constant. But a bigger area with the same density, which is flux per square meter, you'll actually have more flux. So you can set up more flux or less flux for a given length magnetic circuit by just having a larger cross-section area of that magnetic circuit. Typically, we'll have things like armatures of motors rotating inside that magnetic flux. But right now, we just want to see how to create that actual flux. The cross-section area allows you to get more flux lines in there for a given amount of amp turns per meter that's driving this, producing this flux. We want to know, that mu naught there is the permeability of free space for a vacuum or really any non-magnetic material. If you have a magnetic material, then we need another value here, which is some multiplier, so that we can get a permeability of the particular material. So that's a relative permeability. So for magnetic materials, this number is quite high, maybe 400, 500,000, a few thousand. So that a metal material is much easier to set up a magnetic field in than just in a vacuum, because you can have a theoretical magnetic circuit that just comprises air. Okay. Also, then you don't have very good capturing of the flux lines that tend to spread all over the place, whereas a metal path forces the magnetic lines to follow that metal path, not too much leakage. Okay, so what else? These graphs just show you how, by providing a certain amp, effectively it's amp turns per meter. Often the axis will just say amps per meter, but you can either visualize it as having one turn with all those amps forced through it, or rather a smaller number of amps times a large number of turns. So some texts will call it amp turns per meter, but just amps per meter, it's the same thing. Really, it's looking at the amp turns. So there's different materials, and we can see here we get an effect called saturation, where after we provide a certain number of amp turns per meter, eventually we start to flatten out, and the material doesn't enable us to build much more flux density. So cast iron is flattening out earlier than mild steel is, for example. So these curves get pretty flat eventually. Then we say saturation has occurred. We can force more amps, or even provide more amp turns onto our magnetic circuit, but it won't actually achieve in producing much more flux at all. So it becomes no purpose eventually in providing more and more amps to get not much more flux. So we try and normally operate in a region where we're getting some value for money and not achieving saturation. It's not normally linear though, and we also have this thing called hysteresis, which will be discussed here somewhere. Where is it? So it is actually in the, here we go. It is actually in that electromagnetism lesson as well. Hysteresis, basically, this is the graph here. When we magnetize something for the first time, we apply that amp turns per meter quantity, and it will start to produce flux or flux density. After a while, it will start to saturate. When we then reduce the amps, back those amps off, by the time we get to 0 amps, we actually maintain a certain amount of flux density. That's how you'd make a permanent magnet. You'd energize a coil around it, remove that current, and you'd be left with a permanent magnet. The only way to get rid of that magnetism is actually by reversing the current. This side here is negative current compared to the original direction. So if you reverse that current, you'll eventually bring that material down to have no flux in it. And then if you continue to increase the current, but again in the negative direction, you'll eventually saturate it in this region over here. And then if you back that current off again to 0, you'll be left with a magnet now with the opposite polarity, but a permanent magnet. The only way again to demagnetize it, to bring it to 0, is to now increase the current again in the original direction until you bring it to no magnetism. And then if you keep increasing the current, you're going to eventually get a saturated magnet again. So where those curves intersect, it's typically where this curve starts to flatten out anyway. So this hysteresis means it depends a little bit on the history. Are you busy demagnetizing it, or are you busy magnetizing it? So it's not a direct relationship between H and B. It depends on the time as well. Where have you just recently been? You crawl up saturation, or if you stop short, and it won't reverse down that path. Anyway, for our purposes, we will generally not be looking in great detail at magnetic circuits, but we'll know what flux we have per pole, for example, of a given machine, or what flux density we have for a simple coil that's going to be turning in a magnetic field. So don't worry too much about the detail of these hysteresis loops. Right, what else was there? Okay, reluctance. Again, we don't get into detail of calculations about reluctance, but just to tell you what it is. Basically, in the same way as you have an opposition to current being established in a conductor, in an electric circuit, the resistance is basically proportional to the length, proportional to the resistivity of the material, and inversely proportional to the area. And it's a similar thing here. It's just that S is a measure of how reluctant the circuit is to allow flux to be created in it. And again, the longer the magnetic path, that's L meters, sort of center line around a magnetic circuit, the more opposition you'll have to setting up that flux. Likewise, the bigger the cross-section area, the better. So the cross-section area is on the denominator. And of course, permeability is not equivalent of resistivity. It's effectively the inverse of that. It's the conductivity of the material. It's how much does it want to allow, how much does it want to allow magnetic flux to be created. So it's not traveling like current is, but it's still magnetic lines that are present in this magnetic circuit. Okay, so yeah, that's the way to look at it. Here we've got there, what is that? That's magnetomotive force. This is like V equals IR. That would be the same as R, the opposition. The amp turns would be the same as V, which is an EMF. And for the Ohm's law version, V equals IR, we would have this would then be the amount of current that flows. Here, the driving force, it's not an EMF, it's an MMF, magnetomotive force. The opposition is not a resistance, it's a reluctance. And the cause, the effect rather, that's being created by this cause is not a current, but it is an amount of flux. Okay. let's scroll down. We can actually jump to the next chapter, which is, okay, so before we get there, let's just have a look. There are times that we'll have air gaps. So here's an example. We've got a magnetic material. Most of the flux will be traveling through here. There'll be a little bit that tries to escape out of the edges of that air gap. We call that fringing. Effectively, the flux will travel through there. That cross-sectional surface area that we're talking about if you make a slice through here, the flux is captured in this material and it's all traveling through that slice. If you ignore the fringing effects over here, the cross-section area through the air gap portion is the same as the cross-section area of the metal portion. And all the magnetic lines, the field lines, will move, not move, but be present through that air gap. Now, often that air gap can be a little bit bigger, and we might have an armature spinning around there, or some DC machine perhaps. So air gaps are required to allow us good clearance. They don't have armature scraping on the part that's turning inside. But we try and keep those air gaps as small as possible. Put that a little bit better, because the air gap has a very, very high, it adds a very high opposition to the establishing of the magnetic flux in that circuit. We looked at these permeability of magnetic materials, and they can be thousands of times higher than air. So 1 millimeter of air gap might be the biggest factor and the biggest opposition to setting up a flux in your circuit. Right, let's jump a bit further. So we won't do specific calculations on reluctance and pH curves and all those things. Okay, they probably, yeah, we can include one in the first assignment, but there won't be that much of the focus. The focus is going to be understanding that there's a magnetic circuit that is being set up, and we will then have equations once we get into DC machines where we will need to know how much flux do we have, and for a given amount of flux we will have current in an armature and start experiencing a force according to that flux, to that flux density. So I'll explain that shortly. And that was quick, that chapter. Next one, electromagnetism. What's the important things here? Yeah, in fact, the two formulas that we'll use most in our purposes when we're trying to sort of go to kind of call it first principles, with seeing what the principles of a DC motor in particular are, or that applies to other motors too, is these two. Force is BIL, and there's another one, where is it? That must be in the next section. Where is it? Force is BLI, but there's another one which is the induced voltage is BLV. That must be in the next chapter. Okay, so let's actually just focus on this one here. B is the flux density. I is a current in the conductor that is experiencing that flux density. We'll look at a diagram in a minute. And L is the length of that conductor. Theta is the angle between that field and the conductor that's in that field. So we get straight to a diagram, so it'll make a little bit more sense. I'm going to jump to it. Here we go. Okay, so three-dimensional drawing would have been a little bit clearer to see, but basically we've got a magnetic circuit over here where we've got some kind of an air gap, and the flux lines are passing through there. Looking at it here, we see a dimension over here, but there's also a dimension into the page as well. I took that dimension and the one into the page, I would then have the cross-section surface area that these flux lines are passing through, and that would give me this variable B. I is the amount of current passing along or through this conductor, and L is the length of the conductor that is in this magnetic field. So it wouldn't be the whole length of this thing, it would just be the portion that is seeing this magnetic field. There's a bit of bulging or fringing of these lines that occurs here in the air gap, but we're going to be neglecting those effects, generally speaking. So whatever that dimension is over there, and it steps into the page, that's the same dimension that the flux will be established in that air gap. It's across that surface area. So if we force a certain current through this conductor, we will generate a force. That's the principle of a motor. We want to force a current into an armature. We're going to get a force on that that's going to produce a torque. More about that a bit later. That angle there, we can modify the formula by adding a sine theta in there. But technically, theta is the angle between the lines of the flux and the actual conductor itself. So if those two were actually in line, there'd be no force. We actually need the conductor to be perpendicular to get the max force. Sine 90, of course, is 1. Sine of 0 is 0. Okay, so F equals BLI or BIL, same thing. And the sine theta is for the case where we don't have perpendicular. We actually are going relative to our 0 is there. And the formula technically says a sine 0, sine 90 under the ideal conditions, which is perpendicular to the field. Parallel will end up with nothing. Okay, yeah, so what's happening here is there we're seeing that little cross is like the tail feathers of a dart, so you're looking, the current is flowing into the page, into the screen. If it was flowing out, you'd see it as a little point, a circle with a dot inside. And basically, because the conductor itself has its own magnetic field around it, and it's now inside another magnetic field produced by this magnet in this particular case, you get kind of a bunching up of the lines above the conductor and some subtraction of the lines in the bottom, and it ends up producing a force. That's what we're really interested in. There's a force that's produced. How much force? Well, it depends on that equation. The amount of flux density, current that you're forcing through that conductor, and the length of that conductor. Not the length, not the whole length of the conductor, the length of the conductor that is experiencing the flux. So it's only this portion over there. If we had a conductor which is shorter than this dimension over there, then we must actually use the length of the conductor, not the length of this dimension over here, because it's only the portion that's in that flux that actually produces a force. Okay, we'll see how this gets used shortly for a DC machine. Okay, so where were we? Right, so we know that we're going to get a force produced. That force is always, if this conductor is directly into the board like that, our force will always be perpendicular to it. So we've got flux in one direction, that's this way. We've got current perpendicular to that, and the force is yet again perpendicular. That's where these right-hand rules and left-hand rules come into the mix, because we've got current, field, and force or motion in different orientations. Right, so we can get here, that's where we want to go. A very simple motor would be, we've got a power source here, some voltage, battery stack. We've got a commutator, we'll discuss a bit more about that in due course, but it's going to allow through some brushes which are scraping on a metal surface over here, we're going to have current able to flow through that metal contact, through this side, back through that side, and out again. And so it'll go. Once we have current established, we'll now have a length over here of conductor that is carrying a current. There is a field this way between the north and the south pole. So we have our sine theta story that we looked at earlier would be 1 because our conductor is already perpendicular to the magnetic field. And the force, of course, is always perpendicular to both. So there's the force produced down there. On this one here, because the current in this one, of course, is flowing that way, it goes around the back and it comes back this way. So now, of course, the current is flowing the other way. So from that rule, we will find then that the force is the opposite direction to the other one. Okay, so the force up and down on that coil is zero effectively, because there's as much down as there is up. The rotation effect is not zero. If I imagine a lever arm here and a force, it tries to rotate it this way. Same thing here. If I imagine a lever arm and a force, rotation is going to be that way. I'll explain what I mean in a minute about the lever arm. There we're talking about torque being created. If I have many coils in the same circuit, so I come in here, go around this thing 100 times, and then I come back out over here, then for the same number of amps produced through my external circuit, through the power source, I'll have a lot more length effectively. You can either think of it as a fixed length now with lots more amps in it, or you can think of it as a lot more length with the same amount of amps. But effectively what will be happening is that I will get a little force on each piece of conductor, in each of these coils. I will get a small amount of force. But all those forces are going to be added together to try and make the whole thing turn. So if I imagine that I've got a coil and all the coils are basically glued together, the force produced on each strand or each conductor in that coil, those forces will try and turn the coil as a whole because they're all glued together. And likewise, these forces on this side, I'll have one force on each little piece of wire that I've got there. And those forces again will add together to try and produce our torque. Okay, so that's the operation of a DC motor. We put direct current on it and it will start to try and turn because of these forces produced. That commutator, what is it there for? It's just there to provide a change of polarity or change of direction of the current in the coil. Otherwise, we'll just get oscillation back and forth like this. We won't get rotation. So basically, what would happen here is once per revolution, there's a slice, there's a cut through there. So there's two halves to this simple commutator. And once per revolution, the polarity that this coil sees will change. So at the moment, current is going to come in this left-hand side here, through here and out the right side. If we imagine that this thing is now turned, then the right-hand side here is now sitting on the left. That means the right-hand side is going to see current going inwards. But by that stage, it's physically present on the left, so it'll see the downward force again. So by having this polarity change as we rotate, as we rotate this way, it allows us to keep the same torque orientation so we can get continuous rotation. Otherwise, we just keep bouncing back and forth. If you didn't have a commutator, that's what you would get. Okay, a real motor. Well, let's just look at the next diagram before we look at, okay, this is a moving coil instrument over here, very similar thing. We've got a number of coils that kind of glued together. Each of those is experiencing a force. The force is always perpendicular to the, I'm not sure this is the best drawing over here because they've tried to show that the flux lines are kind of coming inwards there because there's an air gap and then an iron core. So flux tends to not go straight. It tends to get pulled inwards and then stretch outwards again. So it converges and then diverges. But basically, at any point, your force should be perpendicular to the flux that you're seeing over here. So to me, these lines perhaps should look a bit more vertical there and a bit more vertical. Let's just go so you can see a bit more vertical over there. But it's a bit of a funny drawing because they've drawn this coil quite large. So you're seeing it with different angles on it. Yeah. I wanted to say for the motor, basically this is a very simple motor, and a real DC motor is fairly similar, just that we will have many turns in it. And you'll probably have multiple segments on the commutator. And in fact, we won't just have many turns like this, we might have coils or turns which are on this axis and some more on that axis and more on that axis. So there's a whole number of windings scattered around some kind of an armature, which is the part that turns. We call it an armature. So it won't just be turns on one plane. It'll be turns in a number of different planes with multiple segments on the commutator, and we might even have multiple poles or multiple pole pairs. This we'd call it one pole pair, a north and a south, but we could have other poles, pole pairs orientated, for example, vertically or even at angles on these things. So a real DC motor would need to be a bit more complicated, but the principle is that each individual conductor that sees a certain flux, sees a certain amps, has a certain length, will generate to the force that is being produced and all turning. Cameron, hi. I'm busy talking to myself here. Can you hear me?
Is it you, Brendan?
Yes, it's me.
How are you?
Sorry, at the moment it's just you and me. I was just recording the session because it seems like nobody else was able to attend. Josh gave us a call at some point and he just to see if he'd missed anything. So I said no, but I'm going to just record myself anyway so that I can send it to you guys on YouTube. I'm going to upload I'll upload this video to YouTube. So normally we'll be finishing around about this time, but I just kind of sort of recording a little bit later. So don't worry, I'll just carry on here, and then tomorrow I'll send it all to you guys. Hopefully from next week most folk will be able to join, but it seems like this particular time most folk were not able to. So yeah, let's hope that Monday is all good for the majority of folk.
Yeah, cool. Now we'll be able to get into a routine as of Monday then.
Okay, cool. So yeah, sorry I can't chat. Got to carry
No worries. Thank you.
For making a cameo appearance.
We'll see you soon.
All right, go well.
All right.
Cheers. Bye. Okay, so back to me. All right, so all of these things, we need a certain flux density, a certain length, a certain amount of current in that length, and we'll get a certain force. We'll see, I'll show you in a minute the relationship between the force and the torque, because it's the torque in a motor that we're actually interested in. The torque will give us that angular acceleration. Force is less of a concern than the torque. A couple of points just to bear in mind. Yeah, if this coil poked right through here so that it was too long relative to these flux lines, the length to use would just be the length of the pole, the magnetic face, the metal face of that material, because the parts that poke through are not doing anything. There must be some flux there to generate that force. Likewise, this portion of length of conductor over here We can exclude it from our calculations completely. Why? Because it happens to be not perpendicular to the flux lines. The flux lines are going across here. That thing is at the same angle, sine theta, therefore, for that piece of wire here, that conductor, theta for that one is 0. Sine theta is therefore also 0. So this does not contribute to any force being produced. Likewise, these two little bits over here, they are also parallel to the flux lines, so they don't produce any force either. And these bits that are sitting outside here don't produce anything either because they're sitting outside of the flux lines which are passing from the North Pole to the South Pole. I'm going to just sketch something up for you on one note here because it's easy to draw on. So if I go here, you'll see me disappearing and coming back every now and again because now I'm going to be quite close to the screen. What I wanted to point out is if you have a conductors like that, let's imagine that those are part of a coil that's going into the board. If I have current going into one of those and current going out of the other one, and I've got flux lines going across like this. So let's say there's a magnet pole there, magnet pole over there. Depending on which one's going into the board, which one's coming out of the board, one of them I'm going to get a force. Color here. One of them I'm going to get a force, let's assume, upwards, and one of them I'm going to get a force downwards. One's in and one's out. And depending also if I've got north on the left or south on the left. I'm not worried about the direction so much as the magnitudes for now. So these forces will always be in the direction shown. They'll be perpendicular to the flux and perpendicular to the conductors that are in that flux. I want to give it a 3 dimensions. I can. Whoops, should have used a different color. For 3 dimensions, I'll be sitting like that. All my flux is going across there. What area would I use if I wanted to work out the flux density? If I had an amount of flux and I want the area to use, I would use this dimension and that dimension. This one here doesn't matter, doesn't make any difference. Once I have a certain amount of flux established and a certain cross-section area, I can go B is flux over area, and that's it. Not the neatest looking equation, but anyway, you know what it's supposed to be. But this gap does actually, the size of that gap between the magnets does actually make a bit of a difference, because for a real circuit, if I continued this magnet down here, for example, I'm losing my 3D, but anyway, if I put coils around this to actually form an electromagnet, not a permanent magnet, I'd have to have a lot more amp turns in here to get the same amount of flux. So it is important to keep that air gap small if you can. But if you have a certain amount of flux and therefore a certain amount of flux density, that dimension there actually doesn't really matter. Okay, but it's harder to establish that same amount of flux if you have a big air gap, because then you need more driving force, more amp turns per meter. The per meter would be per length of the magnetic path. Okay, it's a bit of a crude drawing, so I'm going to just jump over here. So what I want to point out now is how to calculate a torque from a force, because a motor needs a torque. So if we have one, let's draw again, if we have one conductor there and one conductor there, and if we have a force on the one and a force on the other, you might or might not know the mechanical principles involved, but if you can imagine a point of rotation over there, and we imagine a lever arm, I'm going to use a different color. what we call a lever arm in mechanical terms over there, and another lever arm there, mechanical terms, and some kind of a fulcrum over there. So if that was a coil with a fulcrum in the middle, the thing is now spinning around. What happens is if we've got a certain force there and a certain force there, the torque produced is always a force times a distance. Now, the question is, what distance? So basically, if we look at causing rotation around the center point over there, if we, for any, let me just go to, I just want to go to first, instead of a diagram that's got two on it, I want to just show you for one. If you have just anything with a force on it, if you want to establish the turning action relative to some reference point, let's call it, all you need is the dimension of the distance between those and the force itself. We call that the lever arm. So it's a lever arm over there. And that's the force itself. So if that was a little distance, perhaps d or r or some variable like that, that'll give us the turning action. But something important to note, that lever arm, we need it to be perpendicular to the force. So the definition of torque is force times distance, but that distance must be perpendicular to the force. If it's not perpendicular to it, all we need to do is we must find the component of it that is perpendicular. So for example, if I had force here and I have a lever arm over there, that's the force. Let's call this thing R for the lever arm. I can't use this whole dimension. Let's get another color here. Why can't I find another color? Blue. I can't use this whole dimension here. I'm only entitled to use the perpendicular portion. So if I go back here, I can use this portion here. If I resolve this, getting a bit messy, but if I resolve that thing into a portion of lever arm, a portion down here and a portion over there, then the torque that's produced around this point that I was interested in over there, it depends, it's only created by this perpendicular lever arm here, and anything that's on the same line as that pivot point doesn't produce any force. So I either need to take my real lever and apply a little bit of trigonometry to get the portion of that lever that is perpendicular to the force. Or if you want, I can redraw this thing. Or if you want, you can say, there's my force, there's my lever, and I want to use the whole lever's dimension. That's fine, you're entitled to do that, but then what you must do is you must take the force, and the force needs to be resolved into two components. One, change color. One perpendicular to the lever arm, and the other one parallel to it, so parallel to that. If I then just take this portion here, now I can take this force and I can multiply it by the whole lever length R, and I'll also get the torque. So you either take the portion of the force as a vector, which is perpendicular to the radius, which is taking you to the point that you're trying to establish turning action around, or you take the whole force, but then you take the perpendicular portion of the lever arm, not the lever arm itself. So either of those will give you the same effect. At the end of the day, it works out that if you've got an arbitrary lever arm, and I'm trying to find torque around that point, and you've got an arbitrary force over here, you just need to take the magnitude of the lever arm, the magnitude of the force, and the angle between them over there, and your torque produced will be the whole lever arm times the whole force times, let's see, if that angle is there, we want the sine theta component, don't we? Where that's theta there. Sine theta component, why do we want the sine theta component? The sine theta component is going to be, if I look at this force vector, if I look at a triangle here, if that's the hypotenuse, sine theta is this one over here. And I want that one because I want the portion of this force which is perpendicular, and I know the portion that's not perpendicular acts through that pivot point and does nothing. You need a lever arm so that the force will give you a torque. So basically that's the simple formula over there. We just need a force, a radius, and the angle between them. And theta will range from 0, and sine theta is 0. So if my force was in this line, exactly in the same line as this point that I'm trying to get turning action around, I get no turning action. But as I sweep my force more to the right until it's eventually perpendicular, now I will get the maximum once it's perpendicular here. My lever arm and my force, when they're perpendicular, then I get my maximum torque. So bringing this back to a motor, basically I've got a force here, whoops, go again. I've got a force there and a lever arm there and a 90-degree angle, and that's giving me some torque. And I've got another force, another lever arm, 90-degree angle, and that's giving me more torque. And basically I can add those together. So I've got one distance variable d there and another distance variable d there. I can add those together because both are, if they're glued together, those two wires, as if they were part of a turn, of a coil inside an armature of a motor, they would then be glued together and they would both contribute to the turning action. So I can add them together. And if I had 100 conductors down there and 100 conductors over there, each of those, and they each carried amps, each of those would produce a force. And all those forces times that same distance lever arm would produce more torque. Something to bear in mind though is what happens when we're not perpendicular. Let's go down a bit more. So if our flux lines were like this, if our flux lines were like that, because we had a magnet there, and I've got a coil that's, let's say, in this orientation, with a pivot point in the middle over there somewhere. What's the direction of the force on each of these? This is just a pivot point. What's the direction of the force? The force is not like this. The force will always be perpendicular to the flux, perpendicular to the conductor itself, which is going into the screen. The force will always be straight up or straight down, depending if its flux is this way or the other way, if the current's going in or out. And the other one, again, we're going to assume that if the one's going in, the other one's going out, it's going to give us a force this way. It's also going to be perpendicular to the flux. So the force is not affected by the fact that the coil is at an angle like that. It would be affected if the coil was tilted inwards, because then not the whole length of the coil or the conductor is seeing that flux. But if it's just like that, if the flux is there and the coil is there, it still sees the full length of it is still inside the flux, and it still sees the whole force. But the torque is going to be reduced, because basically what's happening now, our lever arm is not this whole length over there anymore. Our lever arm, if we project that force there, it's the perpendicular portion. So it's this dimension, not this dimension. If the coil had been if I imagine this thing was part of an armature, if the thing had been sitting in the middle, not up at an angle like that, then that conductor would have been here, and this conductor would have been there. Now the forces would have been the same, but now the lever arm is longer. So there's more force, not more force, more torque is produced when we're at that middle position. And as you go higher, 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 so the angle's becoming affected, and eventually if you got to the top, right at the top, what would you have? You'd have one conductor there, one conductor there. There'd be a force up on the one, there'd be a force down on the other one. The line of action of those two forces happens to go right through our point that we're trying to achieve turning around. So the lever arm effectively is shrunk down to 0, and we're going to get no torque. So if we put the coil like that and we provide power, current into it, it won't try and move at all. If it's on its side like that, it'll try and move the most. Right, in reality, of course, the coil keeps turning. So if we did a torque analysis on this thing, in the middle it would have a high torque, the torque would be reduced, come down to 0. And then the commutator must switch over the polarity, switch over the current direction inside the coil, so that our torque continues in the same direction. Again, it will grow until we reach horizontal, and then it will diminish until you reach vertical position. And the polarity must change again, and it will build again towards the middle. So we'll have a sine wave of the torque production. But in a real armature, you'd have conductors all over the place. There's lots of them all around. So there's always some which are down the side here, experiencing a nice high torque, while other ones which are near the top here and don't have much lever arm are not experiencing or not contributing much to the torque. So the torque that the armature as a whole sees, since all of these things are glued together effectively, is a relatively smooth torque, even though each individual conductor is contributing even more or less to it, depending if it's near the middle or near the top. Okay, and as I mentioned, sometimes we have more magnetic poles with more flux. Perhaps a more realistic one is something like this. Flux would tend to come through here and out there, and through here and out there, and through there and out there, and through there and out there. So that kind of a pattern we could have, so that there's a number of poles, not just one north and south. But nevertheless, each individual conductor, wherever it may be, if it sees a flux like that, it'll give a force like that. There's one over here, the flux happens to be like that, the force would be like that. And at any point in time, we can analyze the amount of torque that's being created by each of these conductors. All right, then there's another principle, which is the principle of production of voltage. Let's look at that one. That's in the next, the production of voltage if you've got a motion of a conductor. So that should be here somewhere. Next little bit. There it is, yeah. So electromagnetic induction. What we're looking at there is, the important thing really is, can't see it there. It's nice. Touchpad. The important thing is this, instead of F equals BLI, we're now going to look at E equals BLV. What we're up to here is we want to know what EMF is induced when we move a conductor through or perpendicular to a magnetic flux density. Okay, so we now have a velocity involved, we have a length of the conductor, we have a flux density, and we have an EMF produced between the terminals or between the ends of the conductor. We also want to appreciate this one. Whoops, what's happened to it? This one here in particular is important as well. There's basically a fundamental principle that says when we have a rate of change of flux, it's d flux by dt, it's rate of change of flux, expected time. When we have n is a number of turns, when those number of turns see a certain rate of change of flux, we actually end up with a voltage induced across it. In fact, that formula there really is more fundamental, and it gives rise to this one. What's happening here is that if we have a velocity where a conductor is moving across flux lines, we talk about the conductor cutting the flux lines. There's flux that is changing relative per time unit because it's moving perpendicular to it. So that's the simple formula, but it actually comes because the velocity of a conductor moving perpendicular to flux lines actually produces a change in flux experienced by that conductor, which is the same really as this formula, which is each turn, if it sees a change of flux. So that change of flux can be caused by the flux itself increasing or decreasing for some other reason, or by motion of a conductor when it cuts those flux lines. So increasing or decreasing of flux produces flux lines to be cut. This is the term that we use. It's a change in flux that it sees. But yeah, you can get it in two ways, either by imagining a coil with flux increasing and decreasing, and therefore the lines, the wire sees changes, or you can imagine it as if either the field is moving or the wire is moving. Again, the cutting flux lines, it's a change of flux per time unit, and you'll get a voltage induced. So the important part for us here is, again, we have three axes. We've got a relative motion, we've got an induced EMF, and we've got a magnetic field. So there it is there. These are flux lines. From B is flux divided by the cross-section area. The area would be that dimension times that dimension. Don't forget square meters you'd have to use to be SI units. And what they're saying is the length of that conductor that's in that field and the velocity that it has traveling perpendicular to that field gives you a voltage induced between that end of it and that end of it. So if you took a voltmeter here and you tied it from that point to that point, you would actually measure an EMF being produced. And the faster you slide that conductor between those poles, the more voltage you would see being induced. And the longer this conductor, the more voltage you'll see being induced. But of course, when I say longer, we'd need the magnet to be longer as well, because any part that sticks out and doesn't actually cut any flux lines won't do anything. If it was a shorter conductor, so that it didn't reach the full extent of this flux, some flux would just end up not being cut. It wouldn't affect it. So the length to use in our formula would be then the length of the conductor itself. If the conductor poked out past the ends of the magnet, then the length to use would be the length of the available flux. Right, so basically that's the principle of a generator. It's that when with the generator, you are forcing an armature to turn in a magnetic field. So you're producing a velocity where conductors are cutting flux lines. You're going to end up with EMF induced in those coils from this principle. But I think I'll leave it there and I'll talk about it some more next time. An armature, a motor and a generator really have the same physical structure, and both actually experience EMF being induced and forces being produced or applied to it at the same time. Just the direction of these things is different if you've got a motor versus a generator. So next week we can look more closely at that. We'll look at how an EMF is produced according to this VLV formula, how that relates to a coil that's busy moving. For a certain angular motion, we will have a certain velocity that those coils are seeing, and we will then get a voltage induced, and that voltage will be induced whether the thing is a motor, we can call it a back EMF, it's trying to oppose the battery that's causing the thing to turn in the first place. If it's a generator, we just call it a generated EMF, but really it's the same thing. Okay, so I'll call it a day there. I'm going to stop the share, and tomorrow I will be able to put this up on YouTube. It takes a little bit of time because there's got to be a file conversion process that happens on the computer that I'm using here, and then also uploading onto YouTube takes some time as well. So I'll send you a link tomorrow once that is done. And I'll probably send I'll post to the forum a link to this YouTube video of this session, and in that forum post I'll probably give a bit more outline there as well on things to focus on in preparation for next week's session, and just want to go over in terms of the stuff we've covered today. All right, see you then. Hopefully on Monday we can have everybody joining us for the Zoom meeting. Thanks. Cheers.